Let's take a look at the 0.1 microfarad MLCC, which is the most commonly used for noise bypass in circuits or systems. It was explained to some extent in the MLCC section. But let's review the ESL and ESR of capacitors, bypass and decoupling, and learn about the 10x rule that applies when using multiple bypass capacitors, and verify it through actual simulation. An ideal capacitor would have only pure capacitance components. But MLCCs have pure capacitor C as well as small resistance components R and inductance components L due to their internal physical structure. All conductors have small RLC parasitic components. And while they do not have an effect in the low frequency range, they can have unintended effects in the high frequency range. In particular, MLCCs, which are widely used for noise countermeasures, mainly deal with high frequencies, so it is necessary to consider such parasitic inductance and resistance. In this way, all conductors have small resistance and inductance components that are very small but correspond to parasitic elements. That is, since the internal electrodes laminated between ceramic dielectrics are conductors, there is a parasitic resistance R and a parasitic inductor L in one MLCC. These parasitic elements R and L have a parallel structure equal to the number of laminates. So the resistance converted into the parasitic resistance of all layers is called equivalent series resistance, ESR. And the inductance converted into the parasitic inductance of all layers is called equivalent series inductance, ESL. In other words, in addition to the original capacitance, an MLCC has unintended ESR and ESL. Generally, designers only consider the pure capacitance value because ESR or ESL are small values, but in high power or high frequency ranges. These parasitic components affect the operation of the circuit, so if they are not considered, the intended function may not be performed, which may cause unexpected results. Generally, the ESR of MLCC is 10 milliohms or more, and the ESL is several nanohenries or less. The larger the MLCC size, that is, the larger the package, and the longer the internal electrode, the larger the ESR and ESL. In other words, electrolytic capacitors with long leader wires or aluminum or tantalum capacitors with large packages have a larger ESL than MLCCs. The smallest package MLCC has a smaller ESL. And even within the same MLCC, the smaller the package, the smaller the ESL. Looking at the change in impedance according to frequency due to ESR or ESL of MLCC. In the low frequency range, it acts as a normal capacitor with the impedance decreasing as the frequency increases. But as the frequency increases, at a certain frequency, the original capacitance C and the parasitic inductance ESL are in a series structure, causing series resonance and a short circuit, so only the parasitic resistance component, ESR, acts as impedance. The frequency at this point is called the self-resonant frequency, or SRF. SRF has the general LC series resonant frequency formula, that is, the relationship of 2 pi root LC, 1. When the self-resonant frequency, SRF, is exceeded, the original function of C disappears and the characteristic of parasitic inductance ESL, that is, the impedance increases as the frequency increases, takes on an unintended function. Therefore, this area has inductance characteristics rather than the role of a capacitor, and loses the noise bypass function. Therefore, a countermeasure for this is necessary. In other words, you need to apply a type with very low ESL, or apply 2 or 3 or more MLCCs in parallel to shift the self-resonant frequency SRF to a higher frequency range as much as possible, thereby expanding the frequency band of the capacitor's operating area. In the application of noise-removing capacitors, The reason for adding MLCCs with capacitances other than 0.1 microfarad and connecting them to the power pins of the IC is to upwardly shift this SRF. In addition to traditional MLCC, SMD-type capacitors include various capacitors with low ESL characteristics. Depending on the internal physical structure of the capacitor, special capacitors with low ESL characteristics, called LICC, SLIC, 3T-cap, and VLC, are supplied, and these capacitor types are applied to circuits or systems that are very sensitive to noise. Looking at the general trend of ESL values by capacitor type, we can see that MLCC has a value of over 100 nanohenry, and the larger the package, the larger the value. Therefore, we can understand that a smaller package is advantageous for countermeasures against high-frequency noise. Low-inductance ceramic capacitor, or LICC, is a vertically elongated package that reduces ESL, and has an ESL value of 60 nanohenry. It has the characteristic of reducing ESL by half compared to MLCC. This type is also called a flipped or reversed capacitor, meaning that it is turned over. In addition, there are types called SLIC, 3T-cap, and VLC, and you can see that they have very low ESL characteristics of about 20 to 40 picohenry. For applications that require effective low-noise design, the 3-terminal type, or 3T-cap, of these special capacitors from Murata, TDK, and Samsung Electro-Mechanics is mainstream. When comparing the impedance characteristics of MLCC, LICC, and 3-terminal capacitor of the 1005 type, the blue curve for MLCC has the lowest SRF, followed by the green curve for LICC and the red curve for the impedance curve of 3-terminal capacitor. The 3-terminal capacitor has the lowest impedance in the high range, so it has the best noise reduction characteristics. In general, one 3-terminal capacitor can have the same effect as designing multiple MLCCs in parallel. And for noise countermeasures exceeding 1 GHz, it is difficult with general MLCCs, so a 3-terminal capacitor must be applied in the pattern and via processing must be designed in detail. When designing the layout and PCB pattern of MLCCs for bypass, keep in mind that the inductance per millimeter of PCB pattern is generally about 0.5 nanohenry, and each via has an inductance value of 0.1 nanohenry. Therefore, MLCCs for bypass should be placed as close as possible to wide power lines, and multiple vias should be used to connect to the ground layer to minimize parasitic inductance caused by patterns or vias. Since the ESL of general MLCCs is approximately 0.5 nanohenry, which is almost the same value as the parasitic inductance caused by a 1 mm PCB pattern, the effect of parasitic inductance caused by such patterns cannot be ignored. Therefore, careful consideration is required in layout and layout. Capacitors are one of the most commonly used passive components. In the application of these capacitors, the terms bypass capacitor, decoupling capacitor, and coupling capacitor are often used. Let's learn about the differences between these terms and how to apply them. Bypass refers to a capacitor that bypasses high-frequency noise components coming from the power supply or other circuits to ground, thereby allowing the IC to operate stably without being affected by noise. Decoupling literally means separation, and it refers to a capacitor used to block and isolate the noise in IC2 from affecting the power line of IC1. In other words, most power lines are commonly connected to multiple circuits or ICs, and this capacitor is used to isolate the noise between the power lines that are interconnected between these circuits. The decoupling capacitor not only suppresses noise going out, but also acts as a momentary current source to the IC, and plays a power stabilizing role by suppressing fluctuations in the power line. It is important to place this decoupling capacitor adjacent to the power pin of the IC. Coupling means connection. When the signal output from the IC source is an AC signal containing a certain DC component, it refers to the capacitor applied when only the DC component must be separated and only the AC signal must be sent to the next stage amplifier. In other words, it is a capacitor with the purpose of DC blocking and signal connection, and the capacity value can be determined according to the frequency of the AC signal. And generally a capacity of several microfarads or more is applied. Capacitors for bypass and decoupling purposes are often used interchangeably because their functions and effects are similar, and 0.1 microfarads are most commonly used in actual applications. This shows an impedance graph according to the capacity of Murata's 1608 MLCC. The minimum impedance point of the MLCC is based on the self-resonant frequency, or SRF. And when looking at the impedance graphs of 1 microfarad, 0.1 microfarad, 10 nanofarad, and 1 nanofarad, the larger the capacity, the lower the self-resonant frequency, and the smaller the capacity, the higher the self-resonant frequency. In other words, if the capacitance is a large value of 1 microfarad, the SRF is low, below 10 MHz, like the purple cover, so the low frequency characteristics are good. But the high frequency inductance characteristic range is widened, so the high frequency characteristics are poor. If the capacitance is too small, such as 1 nanofarad, the SRF will be in the high frequency range of hundreds of megahertz or more, as in the blue cover. And the overall impedance characteristic will have a large value of more than 1 ohm, which is not suitable. So what is the appropriate MLCC value? Although it is an empirical rule, the SRF of the 0.1 microfarad MLCC, that is, the green curve, is in the 25 MHz range. And the impedance characteristics of the low frequency and high frequency bands are suitable for noise reduction characteristics, so it is most commonly applied for bypass or decoupling purposes. Since the frequency range of general noise is mainly distributed in the tens of megahertz range, if you use 0.1 microfarad, whose resonance point is in the 25 MHz range, you can see a certain appropriate noise reduction effect even without precision tuning. This impedance characteristic graph is a graph of an ideal PCB pattern, and an actual PCB pattern has an inductance of approximately 0.5 nanohenry per millimeter and 0.1 nanohenry per via. Therefore, there are recommended requirements such as MLCCs for bypass or decoupling purposes should be placed adjacent to the power terminals of the IC and the patterns should be short and thick. Since the ESL of the MLCC itself is approximately 0.5 nanohenry, the ESL of the bypass circuit, that is, the ESL according to the pattern or via, is usually larger than the ESL of the capacitor itself. Therefore, the ESL according to the circuit pattern or via configuration has a significant impact on the actual noise reduction results. In summary, the larger the capacitance, the better the low-frequency band noise attenuation characteristics, and the smaller the capacitance, the better the high-frequency band noise attenuation characteristics. Therefore, in actual applications, instead of using just 0.1 microfarad, a design is applied that improves the noise bypass characteristics by configuring a value that is 10 times larger and a value that is 10 times smaller in parallel based on 0.1 microfarad to secure a low impedance range from low to high range. This graph shows the change in impedance according to the ESL and ESR values of MLCC and the characteristics according to the parallel combination configuration of the bypass capacitor. If you look at the impedance characteristics of a capacitor with the same ESL according to the capacitance size, as the capacitance increases, the resonance point SRF moves down. This is because the SRF decreases when the C value or ESL value increases according to the relationship of 1/2 pi root LC. In other words, you can see that the capacitance value must be increased in order to reduce noise in the low frequency band. Likewise, if you look at the characteristics of a capacitor with the same capacitance according to its ESL value, as the ESL decreases, the SRF moves to the high frequency range, and the impedance characteristics in the high frequency range decrease. Therefore, you can see that the ESL value must be reduced in order to reduce noise in the high frequency band. Of course, since the resonance point SRF rises as the capacitance value decreases, a smaller capacitance value is advantageous for noise countermeasures in the high frequency band. Looking at the characteristics according to the change in ESR, it is not a factor that affects the resonant frequency SRF, but only acts as the minimum impedance value at resonance. So you can see that the smaller the ESR value, the lower the impedance at the resonance point. In other words, there is no frequency-related change characteristic, and it affects the size of the minimum impedance at resonance. Since low impedance is advantageous, the smaller the ESR value is also advantageous. Now, let's look at a case where multiple MLCCs are applied to increase the effect of low impedance. What happens if n MLCCs of the same 0.1 microfarad are connected in parallel? Equivalently, ESL decreases by 1 n, and capacitance increases by n times, so the resonant frequency SRF does not change according to the SRF relationship of 1/2 pi root LC. And only the equivalent ESR value decreases by 1 n due to the parallel equivalent characteristic of the resistor. Therefore, we can see that increasing the number of parallel connections for the same capacitance has no effect on the frequency band. On the other hand, what if you connect MLCCs with different capacitance values in parallel? The larger the capacitance value, the smaller the SRF, and the smaller the capacitance value, the larger the SRF. If you connect 1 microfarad, which is 10 times larger than the 0.1 microfarad MLCC, one resonance point SRF will be added on the low frequency side, and if you add 0.01 microfarad, which is 1/10 smaller, another resonance point SRF will be added on the high frequency side. Therefore, you can obtain equivalent impedance characteristics like the dotted line on the graph. In other words, you can obtain impedance characteristics that can bypass a relatively wide bandwidth of noise from low to high frequencies. This method of designing the bypass capacitor value in parallel to be 10 times higher is called the 10x rule. Depending on whether the actual noise frequency is low frequency, high frequency, or wide-ranging, these combinations, that is, the number of parallel connections or the capacitance values, may differ. This is a simulation result to view the impedance characteristics through a parallel connection of multiple MLCCs for bypass. These are the impedance waveforms of MLCC 1 microfarad, 0.1 microfarad, and 0.01 microfarad, respectively. The SRF of 1 microfarad, which has a large capacitance value, is the smallest and the SRF of 0.01 microfarad is the largest. The result of analyzing these three MLCCs by connecting them in parallel is the waveform in which the three impedance characteristic waveforms are superimposed and synthesized to become the impedance characteristic graph in the yellow waveform. In other words, it shows the bypass impedance characteristic with a low impedance of less than 1 ohm from the low frequency to the high frequency band, and a wideband characteristic. In practice, it is not necessary to use multiples of 0.1 microfarads like this, and an appropriate value can be selected based on the noise frequency and size of the design circuit or system. However, In order to increase the noise reduction effect through parallel combination, it is advantageous to apply the 10x rule. In addition, the ESL of the MLCC itself is important. But the parasitic inductance of the PCB pattern or via also has an influence that cannot be ignored, so a design that takes this into account is necessary. Thank you. Bye.